Okay. After we learn about how to calculate the genotype frequency and allele frequency, then we talk about the Hardy-Weinberg principle. So it says that the population will achieve the Hardy-Weinberg equilibrium. Again, Hardy-Weinberg equilibrium means that there is no evolution. There's no evolution because there's no change of the allele frequency or the genotype frequency. So when will that happen? When will a population achieve Hardy-Weinberg equilibrium? When will a population does not have any evolution occur? When all 5 conditions are met. So when there's no mutation, no genetic drift, no gene flow, there is a random mating instead of no selection. When all these 5 conditions are met, then the population will not have any evolution and they reach an equilibrium. But the issue is that these 5 conditions, it is almost close to impossible to achieve because there is always some form of mutation occur, a gene will flow, there will be genetic drift, there will be genetic flow. Mating is not completely randomized, and there is always some kind of natural selection occur. Because of that, a population it is almost impossible for a population stay in the equilibrium. So now we will talk about these 5 conditions one by one, so that you know what they are. First of all, mutation. So mutation can cause the change of allele frequency in the population, and mutation is the only source of new variation in the population. So if you want to introduce a new gene or new allele, then it is a mutation, because the other 4 conditions, it doesn't introduce a new allele. It only change the allele frequency. So mutation will give you a new inheritable genetic diversity. Mutation is random. This is important to know. Mutation is random. Mutation is said that some are beneficial, some are harmful, but I can tell you that most of the mutations that occur in our daily life, they are neutral. Most of the mutation occurs that are neutral. So you may not notice that, but we may have mutation in our body. We didn't notice that because the mutation occur and it doesn't do anything. It is neither a beneficial nor harmful. Genetic drift. So what is genetic drift that we talk about? It's the change of the allele frequency of a gene pool because of the random fertilization. There is random selection or assortment of gamete in the population, causes the allele frequency to go to one shifting the allele frequency in each generation. So it occurs in a smaller population. The genetic drift is more obvious, is more significant to observe in the smaller population because any changes in the allele frequency, you can see the expression of phenotype easier in the smaller population. So this is an example. So in this small population of the frog, you have maybe approximately 10% of the frog, they are dark color. Most of the frog, they are green color. But let's say a natural disaster occur, and then it kills most of the green frog, because the natural disaster may destroy all the leaves, all the lotus leaf, so that the green frog, they do not have the advantage of living on the lotus leaf, and they don't have the camouflage of that. Then because of losing the green lotus leaf, then all more green frog, they are being killed, and then you only have 5 green frog left. And then because of the decrease in the population of green frog, the darker frog, they have not increased or decreased, but the decrease in the number of green frog will make the population of the dark frog increase. It's a relative increase. So there are 2 effects in the genetic drift. One is called bottleneck effect. So what we described previously of the different color frog is an example of the bottleneck effect. It kills a large proportion of the population. Because of that, it will change the allele frequency significantly. Another one is called founder effect. Founder effect is like only a few individuals found in the colony, and then their gene represent the fraction of the original gene pool. An example of this is the Amish population. Amish population, they live by themselves. They isolate themselves from the rest of the population, so that the gene pool there is only they only have a limited gene that is represented by the fraction of the whole population of America. So this is another example of the bottleneck effect. So this is actually an experiment you can do. The original population, okay, the gene pool, you have, let's say, this 3,800 alleles, and then alleles, you can call it a different color. The blue color consists of 53%, and then different color consists of different percentage. And then because of a natural disaster, or I would call it the bottleneck effect, because of natural disaster, only a few of the individual can survive of this natural disaster. The natural disaster is like the bottleneck. So it limits only a few individuals survive after the disaster, and then after this, they repopulate, and then they grow, and then you can see that after that, after disaster, only 3 different color, or 3 different color survive, and then the new population will only consist of 3 color. So that's the idea of genetic drift of the bottleneck effect. The next one is gene flow. Gene flow is the movement of the allele between population. An example of that is the an example of this is like a migration of human being. Individual or the gamete go from one population to another population. And migration is actually good because it increases the genetic diversity. Gene flow also keeps the gene pool of 2 or more populations similar. So what does it mean by increasing genetic diversity? For example, America, the United States, it is basically a country of immigrant. So people from all over the world, they come to America to become U.S. citizen, and then they bring in different genes from all over the world and group as a new population. So because of that, it increases the genetic diversity. But in the home country of the different immigrant, their population may consist of majority of their own people. So that's why that is an example of gene flow, increasing genetic diversity. And the gene pool of it helps to keep the gene pool of two or more populations similar, meaning that you have an example after this? Oh no. So meaning that if you have a mixture of the two, if let's say United States has a lots of immigrants here, so that the gene pool will stay more or less the same because of the different population mixed together, so that it will be more resistant to the change of the allele frequency. However, if the other country, they have a very pure genetic, very pure allele frequency, so majority of people, they are from the same gene pool, then any changes in the allele frequency will make the population diverse. Will make the changes bigger.